Hi, everybody. So I had some questions on homework 18B that I figured I'd make a video about. So here we go. This, I believe, is question 8 from your homework right now. So it says three charges are on a line. The left charge is Q1, 2 nanocoulombs. The middle charge is Q2, that's 5 nanocoulombs. The right charge is Q3, that's negative 3 nanocoulombs. It says that the left and right charges are 2 centimeters from the middle charge. And then it says, what's the force on the middle charge? So I drew a diagram here, which is what I recommend you do. Lay out all three charges. This is the negative one right here, 2 centimeters away from, both of them are 2 centimeters away from the middle charge. And so, yeah. Another thing here is that it says nanocoulombs. Remember, nano anything. So in this case, I'll say nanocoulomb. So 1 nanocoulomb is equal to 1 times 10 to the negative 9 coulombs. You can do the conversions. I'll just say right now, like this will be 2 times 10 to the negative 9. Q2 would be 5 times 10 to the negative 9 coulombs. And Q3 will be negative 3 times 10 to the negative 9 coulombs. Okay. The way to solve this problem is that it actually works a lot like what we did with our electric field example that we did in class on Thursday and Friday. So what I'm going to do is I'm first going to act, so to get the forces that are acting on Q2, there's going to be force from Q1 and a force from Q3. So to get these forces, let's see. The force that Q1 does to Q2, well, that's going to be pointing this way because, so this is the force from Q1 because they're going to be repelled, right? So this is going to be repelled by this charge. And then Q3, this charge is going to be attracted to Q3. So again, I'm going to get another force acting on this one to the right. I'll say this is F3, like that. Because that thing's going to be attracted that way. And so now I'm going to calculate F1 and F3, and then I'm going to add them up at the end vectorially, like I did with the electric field stuff. So the equation I'm going to use is that the electric force is equal to Coulomb's constant multiplied by Q1, Q2 divided by d squared. So in this case, we'll start with 1 and 2, and then we'll do 2 and 3. So we'll start with the force from charge 1, that's going to be 9 times 10 to the 9 coulombs constant, multiplied by Q1, which is 2 times 10 to the negative 9 coulombs. So that's 2 times 10 to the negative 9. And then Q2 is 5 times 10 to the negative 9. So it's going to be 5 times 10 to the negative 9 coulombs, divided by the distance between them, which is 2 centimeters, but that's 0.02 meters. So again, make sure you convert. And if you calculate all this stuff, I get, what do we get here? Well, these 9s, negative 10 to the negative 9 will cancel out, so that's nice. So I got 9 times 2 times 5. So 90 times 10 to the negative 9. Divided by 0.02 squared, I'm getting about 2.25 times 10 to the negative 4 newtons right there. So there's that one. Now to do, and this one's pointing to the right, right? So right. And then for F3, it's going to be the same thing. So say F3 is 9 times 10 to the 9, except now it's Q3 is the other charge. So Q3 is negative 3 times 10 to the negative 9. But when we do this, we only take the magnitude. So it's going to be 3 times 10 to the negative 9. And then the other charge is 5 times 10 to the negative 9. Divided by 0.02 again is the distance squared. Let's multiply all this out. So I got 3 times 10 to the negative 9 multiplied by 5 times 10 to the negative 9 multiplied by 9 times 10 to the positive 9 divided by 0.02 squared. And this one I'm getting 3.38. So 3.38 times 10 to the negative 4 newtons. And then this one's also pointing to the right. So direction, you use this to deal with your direction. And then basically now I'm just going to add these up. So this is going to be the total F net, the total force is going to be F1 plus F3, which will be 2.25 times 10 to the negative 4 plus 3.38 times 10 to the negative 4. And so that means then F net is going to be 2.25 plus 3.38. I'm getting 5.63 times 10 to the negative 4. Or somewhere around there. So there you go. That's how you do that one. All right. Now to one. So this one I could do much quicker, but I'm going to go into a little bit of why I'm doing what I'm doing. But this is number 14, I think, on your problem set. So it says the force between two charges is 4 times 10 to the negative 9 newtons. The magnitude of one charge is reduced by a factor of 2, and the distance between the charges is reduced by a factor of 2. What is the new force between charges? So to kind of go into an explanation of why I'm doing what I'm doing is first I'm going to show you Coulomb's law. I'm using Coulomb's law here, and what this thing is basically saying, what this first part is telling me, is that the force between two charges, and they're going to be some distance away, is 4 times 10 to the negative 9. So what I did is I made up charges that will give me this result. So this is here 8 over 3 times 10 to the negative 9 coulombs and 4 meters. So if I plug those things in there, like I'll do right now, so I got 4 times 10 to the negative 9 is equal to, this is 9 times 10 to the 9, and then if I do each charge is 8 over 3 times 10 to the negative 9, if you plug all this in, you're going to get, well, here, let me plug it all, let me multiply it all up. And then 4 squared, right, because distance squared. Okay, so you're going to get 4 times 10 to the negative 9. Just to show it to you without a calculator, though, 10 to the 9 and 10 to the negative 9 will cancel out. So then I got this 10 to the negative 9 left over. I'm going to leave that off to the side. So over here, I got 3 times 3. Those are in the denominator there. Those will cancel out with the 9 here. So like that. And then what I'm left over with is 8 times 8, and that's 64. So, and then 4 squared is 16. So 64 divided by 16 is 4. So 4 times 10 to the negative 9, that's what this answer is over here. So that's just showing you that this works. This works what I just plugged in, and I cooked it to do that. And now with these numbers now, it says I have to reduce one charge by a factor of 2. So reducing 8 over 3 times 10 to the negative 9 by a factor of 2 is essentially going to give me 4 over 3 times 10 to the negative 9. So it's going to be 4 over 3 times 10 to the negative 9. That's reducing that by a factor of 2. So that's reducing the one charge by a factor of 2, but I'm also going to reduce the distance by a factor of 2. So if my distance is 4, reducing it by a factor of 2 is going to be, so my distance reduced by a factor of 2, that's going to be 2, right? So this new distance, so basically this new charge, I'll call this Q1 prime. This is going to be my new charge. My new charge is this, that's reduced by a factor of 2. And then this I'll call D prime. This new distance is going to be 2 meters. So this is in coulombs. And now let's replace all this and see what new number we get. So I'm going to put all this into Coulomb's law here and see what I get. So Coulomb's law again is 9 times 10 to the 9. That's the K constant. This new charge is now 4 over 3 times 10 to the negative 9 coulombs. And then this is still 8 over 3. Q2 is still 8 over 3. That one didn't get changed. Divided by, and now instead of 4 squared, it's 2 squared. So let's now see what this new value is going to be. Again, times 10 to the 9 cancels with times 10 to the negative 9. If you want to calculate all this out, you are free to do so, and you'll hopefully get the same answer. But I'm just doing this now without just a calculator. So 9 and 3 times 3 is 9, so those will cancel. So I have left over here 8 and 4. 8 times 4 is 32. So I got 32 times 10 to the negative 9 divided by 2 squared is 4. So this is going to give me 32 divided by 4 is 8. So 8 times 10 to the negative 9 is my new thing there, is my new thing. So that seemed like, I needed to know these values, plug them in, and then I could change things. That seems really, kind of difficult. What about, is there a faster way I could do this? Well, yes, there is, but it does require a little bit more kind of thinking in order to do this. So let's paste this back in here like this. So we got this. So I know all of this. So I know like all of this, KQ1, Q2 is equal to this, right? So what I'm going to do now is say, all right, we said before, right, Q1 prime is reducing Q1 by 2. So it's Q1 divided by 2. And then D prime is equal to, well, just D divided by 2, right? I'm reducing Q1 by 2, and here I'm reducing the original distance by 2. So if I do that and kind of plug in this new back into Coulomb's law, so again, I'm going to use Coulomb's law, but now instead I'm going to say KE Q1 prime times Q2 divided by D prime squared. So D prime is in there squared. And now I'll reduce it. I'm going to plug in this into here, and I'll plug in this into here. Because that's what those things are. So I get FE is KE, and then this is going to be Q1 over 2 times Q2, and then divided by this new distance, which is D over 2 squared. Now I can reduce this, right? Let's see. This squared is going to distribute. So I can reduce this to actually being KE Q1 over 2 times Q2 divided by D squared over 4. And then I can reduce this even more, because this is, if I factor out this 2, I'll have 1/2. So that's me pulling out this 2 here. I'll write the 2. I'll put the 2 in red and the 4 in red, just to show you what I'm doing. So here is now 1/2 divided by, and then this is 1/4. 1/4 down here. So that's what's going to get pulled out there. 1 over 4. And then what's left over on this right side is KE Q1, Q2, and D squared. Those are all the original ones. So there's all that. 1/2 divided by 1/4 is actually going to be 1/8. You can plug that into your calculator if you want to. So yeah, 1/2 divided by 1/4, or you could do 1/2 divided by 1/4. That's not true. 1/2 divided by 0.25, that's 2. Sorry, that's 2. Try this again. Or you can multiply by the reciprocal, right? 1/2 times 4 over 1. That's going to be 4 over 2, which is just 2. So, and sorry, this is equal to 2 KE Q1 Q2 divided by D squared. And if you remember, KE Q1 Q2 divided by D squared, as I said back up here, is what the original 4 times 10 to the negative 9 was. So instead now what I'm going to do is plug in, instead of KE blah, 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 is I said, oh, all of that is 4 times 10 to the negative 9 newtons. So I got this 2. So this is equals 2, and then 4 times 10 to the negative 9 newtons in there. Well, 4 times 2 is 8, and I get 8 times 10 to the negative 9 newtons, which again is the right answer. And that's a little bit of a faster way to do this. Yeah, so once again, what I did there is I said 4 times 10 to the negative 9 newtons is equal to all this, is equal to the original thing plugged in. We had our new prime notation, which is that Q1 prime is Q1 over 2. D prime is D over 2. And so I can plug those in here. I get these values. I simplified everything. I get 1/2 divided by 1/4, which is 2. And then I'm left with the original values, which was 4 times 10 to the negative 9. And there you go. So, okay. That should be times 10 to the negative 9. Now on to the last two, which are a little less complicated, so that's good. So we got 2 particles. This one's number 7 on your homework. It says 2 particles, each with a charge, experience a force of 10 nanonewtons. Nanonewtons. They are 30 centimeters apart. What is the magnitude of the charge on each particle? So they have equal charge. So in other words, if I got 2 particles here, I guess let's say they're positive charges, right? So here's Q1, here's Q2, and both of them are equal charge. So Q1 equals Q2, which I'm just going to call Q. I'm just going to call it random Q. We also know the distance between them is 30 centimeters or 0.3 meters. And then 10 nanonewtons. Nano anything is times 10 to the negative 9. So this is times 10. So 10, that's this part, times 10 to the negative 9. Again, you can do that conversion yourself if you want to, but just for speed's sake, I'm going to do that. So this is now going to be, the electric force is going to be Ke, Q1, Q2, divided by D squared. Plugging in now, my electric force is 10 times 10 to the negative 9 equals Ke is 9 times 10 to the 9. Q1 and Q2 are the same, so they're both Q, so I'm going to say Q squared, divided by the distance is 0.3 squared. So lastly now, I'm going to isolate Q. So, well, let's see, I'm going to reduce this first. So that's 9 times 10 to the 9 divided by 0.3 squared. So that's going to be 1 times 10 to the 11. So I got 10 to the times 10 to the negative 9 equals 1 times 10 to the 11, and then Q squared. So basically what I'm going to do is just divide both sides by 1 times 10 to the 11. This cancels with this. And then I'm left with 10 times 10 to the negative 9 divided by 1 times 10 to the 11. So it's going to be 1 times 10 to the negative 19 equals Q squared. So I'm going to take the square root of both sides. And that'll leave me with Q. So the charges are equal to, take the square root of this, 3.2 times 10 to the negative 10 coulombs. So that's the charge right there for each one. All right. So then lastly, it says that a small sphere with a net charge of 3 nanocoulombs. So again, this is 3 times 10 to the negative 9 coulombs. 20 centimeters apart, that's 0.2 meters. So, but anyway, sorry. So 3 nanocoulombs is touch. So this is, let's say, this is the 3 nanocoulomb charge, right? Is touched to a second metal sphere that is initially neutral. So this one's positive 3 nanocoulombs, and this one is originally 0. So if we remember, this was maybe about about last week or something like that. We said if 2 objects come into contact with each other, the electrons will distribute themselves So electrons would flow in here, right? And they'd spread out as much as possible, such that the charge gets reduced in half, right? Or we take the average. So this total charge is 3 nanocoulombs plus 0 divided by 2. So what I'm going to have left over is 1.5 nanocoulombs for each one of these. So after I've done that, so again, the electrons are going to flow into here. So each one's going to have 1.5 nanocoulombs. Let's copy that, paste that right there, and then we'll spread this back out like this. So now each one is going to have 1.5 nanocoulombs of charge. And they're separated by a distance of 20 centimeters, or 0.2 meters. Right, and now I can calculate the electric force on them using Coulomb's law. So plugging these in here, the Coulomb's constant is 9 times 10 to the 9. Q1 is the same as Q2, so 1.5 times 10 to the negative 9. And then again, 1.5 times 10 to the negative 9. I could have just as well said 1.5 times 10 to the negative 9 squared, but I didn't. C'est la vie. So, and then divided by 0.2 squared. Let's see what this looks like. Going to calculate it out really quickly. 1.5 times 10 to the negative 9. Oops. Squared. Times 9 times 10 to the 9. Divided by 0.2 squared. I'm getting about 5.1 times 10 to the negative 7. And that would be newtons. And there's that one. So yeah, hope that helped. And then you should be able to see my solutions as well, the 18b on my solutions page. So check that out as well for the other ones that you may have questions about. So yeah, hopefully that helped. All right, take care everybody. Bye.